Welcome to What Does It Take to Implement the Standard Library? My name is Christopher. I am on one of Google's LLVM teams, which for the purposes of this session means that I contribute to both Clang and libc. If you want to talk, please just feel free to shout things out. I will do my best to hear it on the first try. All right, with that said, what does it take to implement the standard library? Well, you need to be able to read what we call standardese, which is the legal definition or specification of the standard, and be able to turn it into something that is usable for a group of programmers who are writing C++. It often looks like regular C++, but sometimes it takes another form, which we'll delve into later on. Now, there are a few things that we would like as developers. I picked 3 things that are hopefully not controversial, those being correctness, good performance, and good diagnostics. We may disagree on which of these things are the most important thing, although I would hope that everyone in the room agrees that correctness is paramount. But these are just 3 things that I think were a non-controversial set of topics to talk about that we can all find some common ground on. So what do I mean when I talk about correctness, good performance, and good diagnostics? Well, in terms of correctness, it comes in 2 flavors. The first is that we want to make sure that our code is correct. It is no good to anyone if when you call vector's empty function, it returns something other than saying that there are no elements in the vector. That would be a terrible API on our part. But it also has another aspect to it in which we need to ensure that your code is also correct, because just like the compiler can give out warnings for when you are doing something that is correct, but not necessarily the best thing to do, the standard library should also be taking this into consideration. It's our job to ensure that your code is correct. And so that's correctness. In terms of performance, there are usually 2 flavors, the first of which is speed performance, the other one is size performance. We're going to be focusing on speed today. It will just keep things a little bit simpler. The standard library is for everyone. And that means that it's a general purpose programming library. And so as a result, it will never actually beat some sort of specialist tool. If you write a very highly optimized vector for dynamic array for your use case, it is going to outperform standard vector at every opportunity. But for a generalist library, the standard library should never be beaten by any other general purpose library. So that means that your vector and the standard library's vector should ideally be within 0% of each other. But that's an ideal. We don't always get to achieve that. And then the final thing that we want to talk about are good diagnostics. So for those who aren't familiar with the term diagnostic, a diagnostic is something that the implementation communicates to the programmer. Typically, we think of these as errors, warnings, associated notes, but there are a few other ways that could manifest. And so the code on screen doesn't compile. Does anyone want to hazard a guess as to why it doesn't compile?
It doesn't know how to print an S.
It doesn't know how to print an S, correct.
You're missing some code.
I'm missing some code, yes. Does not know. So we have not provided the formatter type, so the formatter specialization to indicate how we print an S. And so we have 3 lines of code. A good diagnostic should make you feel empowered to go back to your code and change the code so that way it fixes the problem and you can get on with the job of being a software engineer. Let's check in with how C++ is doing. Oh dear. So this is taken from one of the implementations, and there are 129 lines. I think it goes only down to 64 on screen, which was not intentional, but it takes 20 lines to find out where the problem is in your code, and then another 38 lines to work out what the problem actually is. And I don't know about you, but this is how I feel whenever something like that comes up with 3 lines of code. So how do we achieve these goals? that is the big question of today. And so we're going to start out with some regular engineering practices. These are mostly focusing on the correctness axis. We'll mostly be talking about processes here. Most of these should also feel at least somewhat familiar to you. And so we're going to start out with unit tests. Unit tests are the way in which we ensure each component is functionally correct. And the way in which I like to do this is through test-driven development. Test-driven development is an ideology a philosophy of how to write your code so that way it's always guaranteed to have maximum coverage and from a unit test perspective, be correct. And so the way in which it works is that you write a test and then you implement whatever the test was covering. And I can't really do it very good justice, but Phil Nash has a presentation that he gave at I think it's Meeting C++, where it's called Rewiring Your Brain, Rewiring Your Brain with Test-Driven Thinking in C++. And it's one of the talks that really impassioned me to use TDD. It was a previous one that where it was successful, but because prior to that, I had not really bought into it. I thought it was kind of boring, and it was just something that my university lecturers talked about, and it wasn't something that I wasn't particularly motivated about. Phil really turned that around, and now it's actually something that I even encourage my students when I'm teaching at university to maximize their marks, because it really does help with getting coverage, especially for unit tests. Now, if I'm going to talk about unit tests and tests in general, I can't not talk about All Your Tests Are Terrible, Tales from the Trenches by Titus Winters and Hiram Wright. It is an absolutely hilarious talk that talks about the pitfalls of tests that aren't robust and contrasts them against tests that are really robust and survive the test of time. So, we should look at a unit test. This is a unit test that checks the size of string. And there is a problem with it. Now, I will say, the test is actually correct, and if it was in one of your libraries, it would not be a problem. Does anyone want to guess what the problem is? Okay.
X is 0.
Sorry?
Should a null character be validated anywhere? Or I don't know.
Maybe this last line is incorrect. I'll have to go and double check that. I don't know. It's not Strulane. So the problem is that it was a good guess, but the problem is that this is using catch 2, and catch 2 uses std string internally, and it doesn't really make sense to test std string using a library that depends on std string. Even if it was okay to use it that way, we don't have trust, and that's the key problem here. Because something depends on std string to communicate to the user that something is going wrong, how can we trust that std string is implemented correctly? And if it's saying that everything is okay, is that actually saying everything is okay? So the way in which we get around doing this sort of thing is to either roll our own test framework or just use plain old C asserts, which are very easy to check correct, and then we can go on and ensure that our implementations are correct. Now, I find assert to be kind of inhibiting to the test-driven development framework, but it still can work. You just need to move a little bit slower when it comes to using TDD and assert. Question?
One problem I found with trying to do testing with asserts is accidentally compiling in release mode instead of debug mode.
That is indeed a problem, yes. So the way in which I think libc++ does it, and possibly MSVC's STL, is that there is no real concept of release modes. That way D and debug doesn't end up in the list of macros, except for the assert test, because that one is necessary for ensuring that it's not defined. But yes, so the point was that asserts can turn off in release mode, and that is a problem generally speaking. But for standard libraries, for the two that I just mentioned, there is a way to ensure that doesn't happen. And I think libstd C++ rolls its own fancy suite, so they get around that a completely different way. We also have a problem when it comes to other forms of correctness. So this is a recap of correctness from earlier, where we were looking at a vector that we are accessing out of bounds. And so the way in which we can get around diagnosing these sorts of errors, because it's our job to make sure your code is correct, is to talk with address sanitizer. Is there anyone in the room who is not familiar with address sanitizer? Okay, I see one hand. So address sanitizer is a compiler extension that basically ensures that your memory accesses are correct. And if they're not correct, then it just crashes the program, gives some output like this. And so if you were to use a stack array and if you were to have a stack array of, say, 10 elements and you were to access the 11th element, it would just simply crash and give you some diagnostics. If you were to allocate something on the free store and do it in the same manner and then access it in the same manner, you would again have some diagnostic like this and no more running program. But for something like vector, that doesn't work, because when you access the 11th element of a 10-element vector, you could have a capacity of, say, 16. And address sanitizer will only know that the boundary is on accessing the 17th element, not accessing the 11th element. And so what we need to do is communicate with inside std vector to say, hey, we only have 10 elements. Everything after the 10th element is, in fact, an invalid memory access, and the program should end up crashing. So if you go and write your own std vector in the same way as as std vector is defined, you won't end up with a crash unless you add the machinery to ensure that address sanitizer knows this is the case. And when you're building with libstd C++, you need to ensure that there's a separate macro defined globally, so that way you don't end up with link time errors. Now again, it's our job as standard library implementers to help you identify your mistakes. So what happens when address sanitizer doesn't actually have the ability to diagnose something, such as with accessing an empty std optional? Well, that's where we have hardened or assertion builds. And those are essentially a way of putting in an assert that provides some sort of helpful error message and crashes the program, similar to how address sanitizer works, but for when you violate preconditions, because involving address sanitizer for a precondition violation may not be the most appropriate thing. And so this is something that you can opt into in all of the major implementations, and it checks the invariants. So this is something that will work today. And if you want to learn more about how libc++ does this, Louis Dion has a session, I think at the end of today, that will go into detail about how this works. Now, is this code on screen okay? Does anyone want to give me a thumbs up or a thumbs down on whether or not it's valid C++?
Based on the previous questions, I'd say no.
Tony's saying no.
So we got a temporary lifetime problem.
So the guess is the response was that temporary lifetime problem.
No.
No?
Now, I'm thinking get extra set of parens out there at the end of random device, but I'm rusty on that.
Sorry, I didn't catch that.
I said I'm thinking you have an extra set of parens out there on random device, but I'm rusty on
So
random, so I don't know.
we're constructing random device, calling it, and then random device goes away, and but the generator has all the information it needs. This is fine to my knowledge.
So the generator needs just a seed to proceed from here.
That is my understanding, yes.
That's why it's valid. But why do we need generator at all if we don't use it?
So, I forgot. Actually, no, we don't use it because we've only declared things. We would use the generator we would use the generator after this section of code, but there is a problem on screen. And so it turns out that this code is actually undefined. And the reason that it's undefined is because the standard says that uniform distribution only works for types between the range of short and long. Sign char is not in that range. And so our uniform in distribution is in fact undefined as it is on screen. And so there was a large code base that uses one of the major implementations. They had this sort of code in their test suite. And it randomly broke because from the user's perspective, this is just generating a bunch of 8-bit integers. And so from the perspective of the user, it was okay code. But the implementation didn't have tests for sign char and similar types, and so they had concerns about correctness. And so that meant that they decided to stop supporting it. But that doesn't mean that it's automatically wrong just because it's undefined. Undefined behavior does not mean badness, even though that's what we perceive it to mean most of the time. If we look at the definition of undefined behavior, it says that it's behavior for which this document imposes no requirements. It doesn't say anything about the program not being allowed to have undefined behavior. It doesn't say anything about undefined behavior being invalid code. It just says that there are no requirements. And so rather than saying that it's badness, it more means that the implementation decides if the code is valid. And there is a giant note that talks about how problems can how the implementation can choose for it to be a compile time error, a runtime error. It could choose to ignore the problem, or it could make it a valid extension, provided that it documents it. And so that's just a general summary. The one exception to this is that core constant expressions can't have undefined behavior in them because that is deemed to be a compile time error, and it's noted, I think, somewhere at the very bottom of this giant blob of text. So the implementation had a concern for a lack of tests. Had a concern with the correctness of this due to a lack of tests, and this, but someone was depending on it. And this is essentially Hiram's law in effect. Now, is there anyone in the room who is familiar with Hiram's law? I see some hands. Is there anyone in the room who is not familiar with Hiram's law? I see about as many hands. So let's go with the definition of Hiram's law, which is on screen. So Hiram Wright, who analyzes a lot of code, observed that with a sufficient number of users of an API, it does not matter whether you promise. It does not matter what you promise in the contract. All observable behaviors of your system will be depended on by somebody. Essentially, if you can touch it, then somebody at some point will touch it, no matter how big the warning sign is on the box. And so this is a classic case of Hiram's law. It's basically an inevitable property of software engineering. And in my opinion, it's even an inevitable property of life. Just, for example, when I was, I think, 2 years old, my parents kept shooing me out of the kitchen and telling me not to touch the hot oven. And, I found myself back in there, touched it, and learnt what heat was. So where am I going with this? Well, Hiram's law is something that you need to have a plan in place for. And so there are a handful of, there's really a spectrum of responses that you could have when it comes to dealing with Hiram's law. The first of which is that you prioritize stability over all progress. That is, that if you break someone, you roll the thing back and you decide, no, I am never going to make this change again because it is breaking someone somewhere. And then we have the idea of a temporary rollback, which is a little bit further along in the spectrum. And so what that basically communicates is we're going to roll the thing back because it breaks some people, but we're going to give you, say, a release or two to fix things, and then you'll have to deal with this because we are going to put it back into our release. And then if we move along a little bit further, we have what I call the tiered release, which is where you roll it back slightly, but you provide an opt-in, so that way people who want to depend on it early still get the feature. And then you flip it, so that way, instead of having it be opt-in, you have it opt-out in the following release. And that means that you you still are supporting the people who need a bit more time to move along, but you're not making it the default anymore. It's basically communicating, hey, we're going to remove this in a subsequent version. And then say in the third release, you completely remove it and you've only got the new feature. Then there's the idea of prioritizing forward fix. That's saying, look, no, we want to keep this in because it helps the vast majority of users. We do recognize this is a pain point for you, and so we will prioritize getting some sort of forward fix in, so that way you're not feeling this pain for very long. And then finally, on the very far end of prioritizing progress over stability, you say, look, there's nothing to fix here. You're going to have to work with whatever is in the implementation as it is. Now, my favorite of these 5 responses, there's a spectrum. So the temporary rollback has things both in between the permanent rollback and in between the tiered release. But my favorite of the lot is really the tiered release, because it takes a little bit from the temporary rollback in that we are going to make it opt-in at first. And it takes a little bit from the forward fix because it gives you, the implementer, the opportunity to work out if there is a need for a forward fix without breaking anyone who may actually be feeling some pain. And if there isn't anything, then it just gives those folks a little bit more time to transition, and then it gets everyone to the happy state over time. And so with these responses and the knowledge that Hiram's law is an inevitability, we should probably think about how we can prevent Hiram's law from manifesting in the first place, because the best way to deal with Hiram's law isn't any of this, it's in fact avoiding it in the first place. And so while we can't actually avoid it forever, we can do things to ensure that we reach it at a later point in time. And so the first way we can do this is by simulating user input using fuzzing. Now, fuzzing is a way of generating input so that way we can work out things that our unit tests may not be covering right now. Unit tests only check for functional correctness. Test-driven development helps you minimize that, helps you maximize coverage, but we are human. And so we are not going to always get everything right on the first go. And being human, we're not going to think of everything that everyone could possibly do. By generating new input and seeing what breaks over time, we will eventually tend to having maximum coverage. So fuzzing is something that exposes the holes in your unit tests. That's one way in which we can get in front of Hiram's law. The next thing we can try and do is what's called integration tests. Now, again, unit tests check for functional correctness, but they also do that in isolation. Integration tests are pretty much the opposite. They check that everything works together as a whole. And Hiram's law is eventually going to catch up with you. So the best way to identify it is to build as much as possible with your library as you possibly can. And the standard library is kind of unique in this regard because it enjoys broad usage. Is there anyone in the room who has never used the standard library?
Yeah.
Okay, that's 0 hands. So what we can do is we can build the world. We can just take an operating system and build every single package that's in there. If it uses the standard library, that's great. If it doesn't use the standard library, well, it's not going to break. And this helps us identify problems. So with libc++, FreeBSD is one of the operating systems that you can just build all the packages for. Gentoo is kind of there. I think it's actually almost completely there, but there are a handful of known problems with libc++ in a handful of packages. And so provided you discount those breakages, you do get some really good coverage here. And then for libc++, you get a whole variety of operating systems. And then when it comes to MSVC's STL, the release team will handle this for you because they have a very, very robust process for this. The downside to this kind of testing is that it's very slow. It takes a while to build an operating system and all of its packages. So I see a question.
So do you typically just build the thing or run its tests as well?
Build, run its tests, just try and get so the question was, do you build the world, or do you build the world and then test the world? And the answer is, ideally, you should be testing the world. Sometimes I don't test the world, but there is infrastructure in place for a lot of these things that kind of just helps you out if you forget to hit the run button. And so really we should be doing both build and run. The second question.
Is when you say that you're building everything, is it because some of the OSs already are built with those libraries?
Sorry, one more time?
The OSs are already built with those standard libraries.
So the question is, you saying
are you actually using in contact with Debian or Fedora just trusting that they are building it with this?
I see the question now. Thank you. So the question is, are we trusting that the libraries the operating system is being built with this particular implementation of the standard library?
Yeah.
So different operating systems will have a different default standard library implementation, and that is the one that the operating system says is what they support out of the box. With Gentoo, it's almost two different implementations. But that, we would build the entire operating system and then build all of its packages to ensure that there are no source breaks and that things are working correctly at runtime. Does that answer the question?
I assume that you arrange that when you build it, it's using the library that you're trying to test.
So David has said that we arrange the build such that it uses the standard library that we are wanting to test. That is correct, yes. So for FreeBSD and Debian, I believe those will work just straight out of the box because FreeBSD uses libc++ by default. Debian, I believe, uses libstdc++ by default. With Gentoo specifically, you would need to you would need to arrange it and say, hey, please use libstdc++ or please use libc++, depending on what it is that you wanted to test. Is that a more rounded answer for you?
Yeah.
Cool. Okay. If you have more questions, please find me in the hallway track and I will happily discuss this with you. Okay. So the downside to this is that it's slow, but being slow should not be a discouraging factor because it does give you all the information that you need. If you are releasing your own libraries, I do highly encourage trying to get your hands on as many packages that use your library as possible to see what breaks as early as you can. Because if you can find out before you make a release, that is way less painful than it is after a release for all involved. David.
You can't do this during your continuous integration. You can't do this on every check-in.
No, you cannot do this on every check-in.
You should do it regularly.
But you should do it regularly, correct. Yes, thank you for that clarification. Yes, David is correct in that we can't do this for every commit because that would be horrendously slow and very painful for the developers, but we should do it regularly, on a regular cadence, say on a weekly build to ensure that we have the fastest possible response time. Okay, so correctness is one axis, but performance is something that we do care about. We use C++ after all, and C++ is all about control over performance. And so there are two flavors of performance, and we're only really going to be talking about speed today. So the first thing you need to do is identify your optimization opportunities. Now, we're not really concerned with big O performance in this particular session. We're going to assume that your big O performance analysis is correct, and that you are actually going to have the most optimal algorithm available in your code. What we are interested in today is going beyond that, trying to milk out every last drop of performance before you get it to your users. Or perhaps it is already at your users and you want to make something even faster. And this means that you really do need to understand what your users are doing. You can't just say, well, I'm going to make std sort faster. You need to understand how people are using std sort. And this means that you need to be profiling your code, profiling your user's code, identifying where these sorts of things are actually being used and how they're being used. The how is just as important as the what, possibly even more important. So profilers are critical here Benchmarks are also critical here. You do need to have an A/B test where you ensure that the change you've made, the optimization that you've made, is actually beneficial, and is not a pessimization or even a neutral change. Just it turns out to be a change for the sake of change because it was unintentional. And in order to do those sorts of A/B tests, you need to ensure that all of your optimizations are on when you're running the benchmark. So this means that you should probably have what's called profile-guided optimization on. Is there anyone in the room who is not familiar with what profile-guided optimization is? See a couple of hands, cool. So profile-guided optimization is a build form where you compile your program with some instrumentation, or you have some sort of third-party tool that does some sort of sampling and profiles the program to work out what the usage patterns are. Then you go and recompile it, and the compiler will have extra information to understand which paths are the hottest and will optimize based on that profile data. There's a few different flavors. GCC and Clang call them different things. So if you do want to learn more about this, you may have to look at what your respective compilers do. But it is a really important thing when it comes to doing these sorts of benchmarks. You could find that your optimizations turn out to be pessimizations without both link time optimization and some form of PGO as well. So that's identifying optimizations. And we should have a case study because we haven't seen code for quite a while. So we're going to talk about std vector. We're going to optimize it. Now, a naive implementation that if you are a teacher or preparing an assignment for a class, or perhaps you are the student in said class, is to implement std vector using a pointer to some data, and then you have a size and a capacity, both as integers. And the class requires that you have you use new, the array-based version of new, because that's just what the assignment is calling for. That's one of the learning outcomes. And for that's why you're not using unique pointer here. For the purposes of std vector, though, that is not correct. So std vector, we actually need to introduce this thing called an allocator, which allows us to allocate memory according to some algorithm. It's also something that users can provide. And they also handle construction. So an object is constructed according to the allocator, not according to when the memory is first allocated. So if we go back to here, the t data, when you do new t of 10, that will construct 10 elements at once. Whereas with the allocator, just because you allocate 10 integers worth of memory, you are not going to construct 10 integers all at once. This is important for types that don't necessarily have a default constructor or similar sorts of things. Now, because you're doing some sort of manual construction, you also need to do some sort of manual destruction, and it's a whole thing. But so that's why we have these new things here. And if you look at how things are upstream in all three major implementations, you'll notice that instead of having two integers for size and capacity, you have 3 pointers. You have a pointer to the beginning of the, well, actually it's being mirrored. So you have a pointer to the first element, then a pointer to the last element that's in the vector, and then finally you have a pointer to where the allocation where the allocation has stopped, and then when the end and the capacity are the same, it will reallocate all the memory. Marshall.
You said that the end pointed at the last element.
Yes.
Points one past.
Thank you. Marshall is correct. The end points at one past the last element, which is how iterators work. Thank you for the correction. Yeah. I like to call this one 3 pointers in a trench coat because that's all it really is. Now, it turns out that after some research and some benchmarking, including both LTO and PGO, link time optimization and profile guided optimization, the size-based one is potentially faster and significantly so. Without these sorts of benchmarks, you really don't have a strong idea of what's going on. It's natural to say, well, because we are returning pointers from begin and end, and that's how things work in C++. We use iterators. it seems kind of natural to conclude that's the case. But with benchmarks, it kind of shows that std vector could be a little bit faster, in fact, significantly faster at scale, if you get the right optimizations turned on and then do some amount of profiling and benchmarking all together. And so we should probably talk a question.
So when you're benchmarking against one version of the compiler.
Yeah.
And this version of the compiler has a set of optimizations that it does. So this benchmark might not be true anymore when a new version of the compiler gets new set of optimizations.
Yes. So the point that was being raised is that we are benchmarking things against a specific release of the compiler, and then in a subsequent release, the compiler may do something different, and that could lead to a different result. And so that's why benchmarks need to be run fairly regularly to ensure that things remain as they are.
Yeah, but when you're deciding which version of implementation you're using for your vector or for your class, based on the benchmark, that might change in the future, and it will be a costly proposal to change that implementation in the future. Is that really a good strategy to?
So the point being raised is that that if you move on through time and you have a compiler change. It's costly to go back and forth. So is this a good strategy? And the answer is, I see a hand, David.
Yes. The answer is you need multiple benchmarks.
Correct.
When you're looking to make a performance-related change, you need multiple benchmarks against the multiple compilers with multiple option sets.
Yes.
So that you know you're not causing a regression in some other situation.
David's got a very good point there. Marshall, I see your hand. We'll get to you in a second.
It could still change in the future, and I don't know that there's any way to protect against that.
Yes. So David's point is that you have multiple benchmarks with that are run across multiple compilers, across multiple build options and optimizations to ensure that it's minimizing the chances of a regression. Like, we will never be able to say definitively this is always going to be the best implementation. It's just minimizing that chance. Marshall?
I was just going to say that you have to look at the costs and the benefits very widely for this. Suppose you make a change because it benchmarks better and you get better performance, and then somebody discovers a new optimization technique, because that's usually what happens, right?
Yes.
We won't talk about compiler bug causes a regression. We just get those fixed.
Yes.
Somebody discovers a new optimization technique which makes the old implementation much faster. Okay, and you say, oh, well, we want to revert to the old implementation.
Yes.
Okay, that's a cost. Does that happen that often? Not that often. But in the meantime, you and all your users have reaped the benefit of the optimization that you have put in.
Yes.
And you have to compare the cost of switching the implementation to a new implementation, and whether that be the old implementation or something else that you've come up with, compared to the benefits that you have accrued. And everybody has accrued.
That is a really good point. Thank you, Marshall. Did everyone catch that? Okay, I'm going to trust the microphone that picked it up as well.
Thank you. I love that answer.
That was a fantastic answer. So I've got two hands. I do need to, in the interest of time, continue on. But no. So I'm just going to ask quickly: are those quick questions or comments?
Like ask Marshall's, about Marshall's statement, a question like if it's possible to feature like two implementations in the standard library based on macros and like compiler version, for example.
So that sounds like it's a good thing for a hallway track. Sorry.
Okay.
Just in the interest of time.
Just a quick one to your two different representation of the vector. The one with the size, the size.
Yep.
Imaginary tells you could go up to the size type allows, but that's not true. You have to take in the size of the elements you plug in. With your vector, with your pointer arithmetic, you can't go over it. So I'm pretty sure that the standard will take that into account, that you can't put in a capacity or a size which would overflow multiplied by the size of the struct you put in.
Yeah.
Yeah.
I mean, basically, when you change the size of a vector can only be so big.
Yeah.
And
If malloc succeeds, then malloc
one of the constraints is that basically maximum size t divided by the size of the element.
Yes,
Just the one gives you the impression you could go. The other one simply says
This
never
also
have-
sounds like a really good hallway track conversation. I hadn't anticipated that, so I am going to defer that one to the. I think it's a really good question. Want to continue this discussion, but let's do that after the session, please. One thing that everyone in this conversation has reminded me about, so I'm kind of glad that this conversation did happen, is that if we do apply this change to std vector in any of the major implementations, it's going to be an ABI break. We are changing something quite fundamentally here, and so that goes into the whole spectrum of dealing with Hiram's law, because an ABI break is factors into Hiram's law. libc++, especially, I don't know about the other two implementations, but libc++ has a thing called an unstable ABI mode. And so if this were to be integrated into libc++, it would only be available in the unstable section. Now, I'm not saying that will happen. I'm just saying that if it were to happen, that's where it would be. If you want to be building with the stable ABI, you wouldn't be able to reap the benefits of this, but you would get that had you built with the unstable ABI. Now, benchmarks, we should probably very quickly go through what benchmarks are possible. So there's macro benchmarks, which are like unit tests. They test things in isolation. They give you an idea of what's happening, but that's really all they're good for. Then you have macro benchmarks, which are more like integration tests. They test the whole program, and they give you an indication of how your thing operates in a larger society. And they are influenced both by link time optimizations and profile guided optimizations. This is what I was talking about earlier, where I was doing some benchmarking. I hadn't turned on profile guided optimization. I found a regression in performance and was very confused because all other data had pointed to things looking promising, and it wasn't until I turned on profile guided optimization that we found out that I was just being a little bit silly in my configuration. So the question that you're probably asking at this point is,
So you assume that most of your users use profile guided optimization? That's why your benchmarks are...
The benchmarks want to capture as much information as possible. And so if we're going to make a change for optimizations, we need to know when this is this going to benefit anyone at all? And that's where profile guided optimization helps out. I do encourage using profile guided optimization because it does help. The LLVM documentation, I think, says it improves Clang's build times by about 20%. So I think that's probably all the time we have for benchmarks. Again, I'm more than happy to talk about this stuff in the hallway track. So we're about 45 minutes in, and you're probably wondering, what does any of this have to do with the standard library? And I think it has everything to do with the standard library. I do a lot of LLVM outreach on Discord and try and encourage people to contribute to either Clang or libc++, because we can all use a few more contributors. That is just a property of open source software. And the idea that I get from people is that they think it's kind of like summiting Mount Everest. It's this really difficult thing that only a select few people can do, and no one else is able to do it. People often say they're not ready to contribute to a C++ compiler or standard library implementation, and they're always having to prepare for it. And it just seems like this perpetual cycle. People kind of feel trapped in not being ready for it. So this is Mount Everest, quite near the peak. What I think it's more like is summiting Mount Kosciuszko, which is the tallest mountain on mainland Australia. It is more of a big hill. And there is even a path that goes to the summit. That's how much of a big hill it is. And I think this path is actually quite apt because that is the standard. If the summit is implementing C++, the path is a standard, and so you have a bit of help. Things like Everest are safety critical things, where if something goes wrong, it is catastrophic. With implementing something like Clang or GCC or libc++, that is difficult. You do need some amount of ability with C++ in order to do things, but it's not like a mistake in the standard library or a mistake in the compiler is going to be catastrophic to the point where there will be something like loss of life. It's something that you do need to have a lot of verification for, and that's why we have so many robust tests. But it is something that everyone in this room and everyone watching the video when it goes online is able to do. And the only way to actually get good at implementing this sort of stuff is to contribute. You're not going to be ready to be a standard library implementer unless you try your hand at being a standard library implementer. It's just like when you're learning to program and your teacher said, well, the only way to be good at programming is to write programs. It's kind of a self-fulfilling prophecy is the term. So that's why I think that all these practices are relevant to what it takes to implement the standard library. Having said that, it's not all sunshine and rainbows. And so you do need to understand what you're getting yourself into. And there are a few things that I want to bring to your attention. So we are now a little bit over the halfway mark for this session. And I have not actually articulated what the standard library is yet. We have not had that conversation. Now, on one end of the spectrum, we have people answering the question, what is the standard library, as the collection of headers that ship with the compiler. So vector, math.h, and so on. And then on the other end of the spectrum, we have the group of people who say, well, it's not the things that ship with the compiler, those are implementations of the standard library. What the standard library actually is the set of text in the C++ standard that goes from the library clause all the way to the end of the thread clause. And that is what the standard library is. Now, I think both these definitions are correct depending on your perspective. From a user's perspective, there is no need to even think about what the standard, what the C++ standard says. And from a language lawyer's perspective, well, the implementations are the theoretical thing. The abstract machine is what is important here. So I think there is one thing that that both these extremes can agree on, and it's whatever is in namespace std plus libc. And so that's the definition of that's the definition of the standard library that we're going to work with. It's in std or libc, and we derive that from what's in the standard. Now let's run through another example, and this one's a bit more of a thought example. So I don't really have anything for you just yet in terms of slides. I want you to think of yourself as someone that has been convinced to go and contribute to your favorite C++ standard library implementation. And you've been there for a couple of weeks, you start to feel good about it, and then some feature that you're really passionate about ends up being put up for review, and you're like, yes, I finally get to use this thing in my own code. And so you go and review it, and there's a couple of comments that you have. Like overall, it's a pretty encouraging message. But there's one thing that you happen to say, which is, hey, this thing that I see you're doing here, CPP reference says that it does X, but you were doing Y, and do you want to just walk me through your thought process here? And, it's from someone that you've formed a bit of a relationship with, and so you're really excited when you get an email from GitHub that says that they have responded to your comments, and then it turns out they send you 3 words: don't use CPP reference. And if you receive these 3 words, you're probably feeling like this. So I want to make something very clear. You can still use CPP reference for non-standard library or non-compiler related implementations. CPP reference is an excellent resource, but it does have mistakes and omissions. It is an interpretation of the standard text. And when you interpret something from from CPP reference, you are interpreting an interpretation. And that means that it's kind of like a photocopy of a photocopy. And that is not particularly good when you are providing the implementation of the standard library itself. So we will walk through an example in a moment, but I do want to make it very clear. Everyone can still continue to use CPP reference. I even used it to build some parts of this slide, of this talk, and so it is still a very important thing to use, just not when you're implementing the standard library itself. And so let's run through an example of why that's the case, because I do think this does warrant some discussion. So this is the piecewise constructor, the pair piecewise constructor that we saw on the very first slide after the title card, but it's from CPP reference. And so it goes through the description of what a user can expect for fisted pairs piecewise constructor. Now this is the standard ease from the first slide. Does anyone want to take a guess at what was missing from the CPP reference slide?
Mandates.
Sorry?
Mandates.
Yes, the mandates paragraph is missing. And that is actually a big deal. So let's talk about what mandates means. So to start off with, there are certain words of power in the standard, and these words of power are effectively things in prose that are italicized to indicate, hey, this is a word of power. And it means that it's got more than the dictionary definition of what the word means. So there are a handful that I've put on screen. We'll focus on two of them for now. The first being mandates, which says that the conditions outlined, if they're not met, the program will be ill-formed. Or basically, you get a diagnostic and no program. This does not constitute a valid C++ program. And the example that it gives is that the implementation is allowed to provide a static assert, or in some really rare cases, delete the function using a constraints expression. Sorry, a requires expression, requires clause. I have not found any cases that meet that second example, but there are a handful, I believe. The other one that we're going to focus on is constraints. And that says that if the conditions are not met, then the function can't participate in overload resolution. Basically, you can use requires clauses for something, or use regular old spinner if you don't have C++20 at your disposal, or need to be backwards compatible. And if we compare the two implementations based off CPP reference and based off the standard ease, you may end up putting a requires clause based off the CPP reference description, because it didn't say anything about whether or not putting a requires clause is valid or not, whereas the standard is actually outlining that. And so this is important because it changes whether or not this works. And so I'm still a little bit iffy on why the implementations agree this is allowed, because in all three implementations it says true. I think this might just be a limitation of the implementations. But if we change it from being a static assert to being a requires clause, then it will change the answer from being true to being false. That means that we have a pretty observable change in the program. But you might say, Christopher, this is an esoteric example. It's probably low traffic. The mandates was just slightly forgotten because it's something that isn't particularly well needed. And surely something like std vector doesn't have this problem. One of the most common constructors of vector does in fact have another similar omission. So this is a description of the size-based constructor for vector. And this is again for CPP reference, and this is the standard ease. And notice that if we go back to the CPP reference one, it doesn't identify the precondition. And that precondition is again a big deal when it comes to thinking about the implementation, because you may end up doing something that CPP reference didn't clue you in on. And so that's why when it comes to implementing things in terms of the standard library for Clang, GCC, please don't use CPP reference. Please only consult the standard when implementing C++. Again, using third-party documentation for non-C++ implementation related things is great, and I encourage you to continue using that. Don't read the standard unless you need to. But when it comes to implementing C++, you should consult the C++ working paper. And now that HANA has implemented a search engine for the working paper, that makes using the web-based interface a lot nicer, because you can just type something and find it pretty quickly. Yes?
What about defect reports?
What about defect reports? So that is why I have put the C++ working paper here instead of putting the C++ 11 final draft followed by the 14, 17, 20 and so on. I did originally have this quite longer, and someone pointed out defect reports and how the standard is more of a living body, and so the working paper is the best way to get defect reports in to your implementation as quickly as possible. The other thing is that when a defect report is applied, it is something that you need to decide whether or not you want to backport it, specifically for the standard library. I don't know the core rules about defect reports, but with the standard library, it's a case of the implementations decide whether or not it will be backported. And so that's a conversation that you have to have with each of the implementations. Typically though, I think a lot of things are backported. Was that a from Marshall?
That was a nod.
Yes. Okay, cool. Okay, so we've talked about CPP reference, and I've been throwing this word implementation around a lot. I haven't really talked about what the C++ implementation is. So let's do that. The implementation, at its simplest idea, is that there is a compiler that produces a binary, and there's some runtime support that works with the binary to provide you with something that's running entirely. And so it's just, the simple idea is whatever your toolchain gives you, that's the implementation. But let's break that down a little bit more, because there's a linker as well. And the linker is an important part of the implementation that we often forget. We just kind of bundle up with Clang or with GCC or with CL because those invoke the linker on our behalf. But when we get a diagnostic from the linker, it's often something that we need to deal with, and we are very painfully aware that it's a link time error. So that is something that we should probably integrate into our idea of what the implementation is. It's more than the compiler, it's the linker as well. But that's not the full story, because what's the runtime support? Well, it turns out the runtime support, at least for the purposes of this talk, involves the compiler's runtime support library. For LLVM, that's called compiler RT, compiler runtime. It has the C++ standard library, the C standard library, and exception handling. Even if you're building with F no exceptions, that gets factored in. It just happens to be that there's nothing linked, and so it may as well not be there, but we do need to consider that. And so all C++ programs depend on the existence of these four things. But that's not the full story either, because the C++ standard library turns out that it's quite unorthodox, and the compiler has a say in what defines part of the standard library. It's actually heavily involved in certain aspects of the standard library. And so that's another part of it, but that's still not the full story. We'll come back to this in a little bit, because we're going to pretend that we're only on a hosted environment right now. And so the operating system is another part of the implementation. I'm going to gloss over containers and things like multiple operating systems, virtual machines. None of that is really interesting here. What's important is that there is a host for running the program. That's a part of the implementation. And then finally, the last part of the first I'm willing to go in the definition of the implementation, because it can get quite esoteric, is hardware. And if you don't have a host, then just pretend the operating system box is missing. All C++ programs operate on some sort of hardware. And if you're going to say, well, my implementation is in my brain, well, your brain is kind of hardware as well. So that's the case as well. So there are many layers in the implementation, and it's as a user, it's okay to think of it as compiler, linker, binary, and runtime support. Like, that's fine. But as an implementer, you do need to see things a little bit more holistically, because there are a lot of moving parts. Some things happen at the hardware level. Some things happen in the binary. Some things happen in the compiler, and some things happen in the runtime support section. And you really do need to think of everything as one unit rather than as a bunch of separate projects. Now, we do split them into separate projects because that just makes everything a lot easier on everyone. It would be very, very unfortunate if the libc++ folks also had to go and implement FreeBSD. So that's for practical reasons, but we are working together in an ecosystem that brings you the output that you want. And that's why I like to think of C++ standard library implementers rather than thinking of them as a library developer, as a compiler developer, because the C++ standard library is an extension of the compiler. And so instead of, we do package it differently. That is a very important thing. And most of your work, when you're working on a standard library, isn't going to be hacking on GCC or hacking on Clang. it's going to be working in regular C++ code. But there are aspects of the compiler you have to either interact with directly, or you are going to be extending the compiler in some way. And if you're not going to be extending it, you're going to be filing a ticket to say, hey, can someone please extend this for me? That is also a valid way of being the standard library implementer if you don't want to get your hands dirty inside a compiler implementation. So I mentioned that the compiler has a bit of a heavy hand in some aspects of the standard library. Sometimes implementing things in the compiler is unavoidable. For example, general language features, if they're not made available, you can't use them. It'd be very difficult to use modules if modules didn't exist. Then there's things like is trivially copyable, which is a type trait, and that can't be implemented in regular C++ code. It's a property of a type that can't be detected without first querying the compiler. The compiler has the information, the code does not. And the only way to get that information is to use that is trivially copyable. Then there's things like is constant evaluated, which again is something only the compiler has. All the atomic operations are pretty much done inside Clang, at least. I'm pretty confident the same is true for GCC, but I don't know about MSVC. And then things like coroutine support, that also, and source location, those sorts of things are things that only the compiler can know. Then there's things where direct input from the compiler can be optimal. It doesn't mean that we need to implement them in the compiler, but it is really something that we should consider putting in the compiler. For example, things like std_move can yield a lot better code generation for unoptimized builds when they're put in the compiler. And I believe all the major implementations support std_move, std_forward, std_as_const, and a couple of the others directly in the compiler. So that way when you type std_move, you're not getting some sort of intrinsic. No, std_move is actually just being read as a static cast. Make integer sequence is something that I believe was originally implemented in code, and yes. then it was put in the compiler because it was horrendous. That's only what I've heard, though. I've not looked at the original implementation of make integer sequence. And then printf's interface is also in Clang, probably GCC and MSVC as well. I'll come back to that one in a little bit. And there's a couple of other things that I would really like to see moved into the compiler. We'll only be talking about the format interface one. But really, what you get from this is you get better code gen, you get better debug info, you get better diagnostics. It really does help out a lot. And then there is the natural question from here, well, should we be putting everything in the compiler? The answer is no. Don't put things that don't need to be in the compiler. You're not going to get a lot of benefit out of it. So for example, std_vector really should stay in code. Putting things in the compiler is at least 1 or 2 orders of magnitude harder than writing them in regular C++ code. Because regular C++ code is an abstraction over what the compiler does. If you put things in the compiler, you need to build out the whole AST and all the expressions that are relevant. That's a lot of work. Marshall, did I see a hand?
I was just saying, and if you have all the code locally, it's a lot easier to change when the committee changes its mind or adds things.
Yes, that is correct. So just in case anyone missed that, having it all locally in code makes it a lot easier to change when the committee adds or removes things or changes something due to a defect report. So really, things should only go into the compiler when the benefits are clear. And that brings us to the fourth act of this session, which is the exclusivity of the standard library. The standard library and the compiler have a very close relationship, and that's a unique property of a library. There are very few libraries that can claim they have a relationship with the compiler. Now, there are a handful of other libraries as well, but the standard library is the one that is the most common. Now, what I'm going to focus on in the interest of time is that we want good diagnostics. This is one of the benefits of putting things in the compiler. And this is our friend from earlier on. Let's just check in to see how we're doing. This one's a little bit better, actually. It's from a different implementation. And it turns out that we get the information we need very close to the top. It's still 22 lines of error per code. which again makes me feel like this. That is, a question?
Yeah, for the simple things like this, why can't the standard require like static assert on the type to have the format instantiation?
So the question is, for something like this, why can't we just have a static assert at the instantiation? The thing is that, so I didn't implement print and I didn't review it, so I don't fully have all the information. But my understanding is, well, actually, I think based on this one here, there is a static assert there. The standard does not, it's a little bit hard to read because the text is small, but I believe, so I only remembered as you're asking the question, there is a static assert at the top that does exactly what you've said. But the standard itself doesn't articulate how diagnostics need to be issued, only that they are. And so that is a thing that's left to the implementations. Whether or not that's good is a different kind of conversation, but it is what it is. Does that answer the question?
Yeah.
Cool.
Yeah, I missed the first part. Yeah.
No, that's cool. It is small text. So we feel like this right now. However, that said, it isn't the best kind of diagnostic. Could be a lot worse. In that we don't get a program at all because the developer spent so much time trying to get it into the compiler that it missed the release. And that is worse because now we can't use std_print at all. It's better to get something that is difficult to read and then get your program working, you're having your code not make you want to tear your hair out, than it is to say, well, sorry, you're going to have to wait till the next release or possibly the release after that. Putting things in the compiler is really difficult. And so if you get something into regular C++ code first, you get users using this thing, and then you can iterate upon it, make it less painful as time goes on. We should be looking to the horizon as implementers, but that doesn't mean that we start at the horizon, because the horizon is always unreachable. Now, can we do better? Well, it turns out that printf's interface is checked by the compiler. And that's because printf is a C function, and thus there are limitations on what can actually be checked. And if a format string is invalid, then the program is undefined, and implementations disagree on what that undefinedness means. But typically, it is a correctness problem if your format string is incorrect. And so the compiler steps in and does what the library cannot. So if we can do this for printf, why not for std_print as well? It's similar to what the second example with the static assert showed, but it only contains the relevant information. The entire template stack trace is missing, and that is really nice. It's also more personalized because instead of saying something was wrong, it says that S was missing the formatter. Now this isn't quite what I want. What I would prefer is something that's slightly longer that gives you an example of what you need. Because I can never remember how to implement formatter off the top of my head. In fact, having written this slide, I probably can now. But I can never remember, and there is an extra step if I have to go to CPP reference and find the code that shows me how to do it. Having the compiler just say, hey, look at this thing, that would be really nice. And there are some proposals in flight at the moment to Hannah, you've got a proposal in flight for throwing exceptions in context for contexts. Do you think that would help produce something like this?
Yes.
Cool, thank you. So that is one way in which we can, instead of getting this in the compiler, get the compiler to help library users out. And so abstractions that help us with this are potentially available. But this is a starting point for what we can do in the absence of such functionality. And I do think that we should be using this sort of metaprogramming scarcely, but when we do need it, having those sorts of tooling available is really nice. And when it's not available, punting this stuff into Clang gives users the best possible experience. And as a standard library implementer, I think that it is really our job to provide the best possible experience for our users. I hope everyone agrees. Is there anyone who disagrees that we should be providing the best possible experience?
The worst possible.
Sorry?
The worst possible.
The worst possible experience. I see that you were a yes. Is that a hand as a you think we should not be providing the best experience, or a question?
I think you giving here is like you give a big benefit for the developers who produce this library. But from users' perspective, I don't want to say, oh, tell me there's something missing in the functionality of the library. That I would want something like a more like say suggestions to say, okay, how you correctly use it.
That's what this is.
Yeah, that's what this is.
Cool. Thank you for whoever said that. Thank you. I think you were first, and then.
So there is like a Python-based ChatGPT frontend which would snatch the error and provide a really cool explanation.
ChatGPT.
Bro, not bro, I don't care.
So
it gives even an example how to fix it.
So I'm going to, that is an interesting conversation. I'm going to defer that one specifically to the hallway track. If you want to find me on that one, please track me down. But I think that providing information to the user in the most accessible way possible and not having them met with something that that is 100 lines of error for three lines of code, don't you think that that's a nicer experience?
So the question is like, what is a tooling question and what not?
Mm-hmm.
Sorry, one more time.
The question is like, what is a tooling question and what not?
What is a tooling question and what not? I think both our perspectives are tooling perspectives. It's just a case on how do we surface this information to the user. Now, diagnostics are a real passion of mine, and getting the best possible diagnostics to the user, like say in the IDE or in something that's better than, say, that's more descriptive in the command line, is also a very important thing. That is a whole can of worms I really would prefer to spend an entire separate talk on. So maybe we should definitely talk about this in the hallway track and see if there's something that we could talk about, like say at a future CppNow. Does that sound good? Cool, thank you. Question?
I think it's important to acknowledge that this is a very nice diagnostic for users.
Yep.
But we should not forget about diagnostics for the implementers as well.
Sure.
The current state of diagnostics, it makes no distinctions. It prints absolutely all the information anyone might possibly want to know.
Yep.
But if it's errors just like this, maybe S actually does have a format specifier and the print implementation got something incorrect. And
yep.
So this is a false positive. There's no information right now to figure out why the implementation side of things might be incorrect. So if a tool wants to pursue this type of user experience, I think it's important to also remember to include an option to reveal all the verbosity that we are currently hiding right now.
So that's a really good point. To summarize that, I think that what you're saying was that there is there are two axes. There's the user axis, the implementer axis, and this obfuscates potential implementation problems as opposed to what might be necessary for an implementer. It's at the expense of the implementer for the benefit of the user. Is that a good summary? Cool. I think that is a good point to raise. It is still an open question. It's not something that I have an answer to just now. I have spent quite a few months, well, at this point, years, thinking about how to do that and still don't have a good answer. But yes, that is a very good point to raise and also warrants a separate discussion. I would love to continue that discussion though at some point. So where all this goes to is that compiler extensions are good for the standard library to use on your behalf. I make no judgment on whether or not you want to or do not want to use compiler extensions in your own code. If you do and you are okay with paying the price of another implementation not supporting your code, then that's okay. You've made that trade-off. If you don't want to use the extensions, then that's also okay, because it means that you are prioritizing portability over some sort of niche feature. But in terms of implementing the standard library, the built-ins get you the best possible user experience. And a standard library implementation is an implementation. It is not concerned with portability. That's what the point of the standard library itself is, getting you to use this thing so that way you can go from implementation to implementation to implementation. And so that's why compiler extensions are a boon for the standard library to use on your behalf. It is kind of limited in that it only targets standard, but it does provide you with the best possible toolchain, which again is a goal that we should be striving for. And all of this really, if we wrap up, is a way of me inviting you to join us. Now, what we've talked about is that the compiler and the runtime are inextricably linked. You cannot escape that. That's a good thing. That's actually really good for users. Our engineering practices are basically the same as yours. They may be a little bit more rigorous. We may do some more things than you, but we're still doing tests. We're still doing benchmarks. We're still having to deal with breaks and get you, our users, the same things that you want to get your users. And so what does it take to implement the standard library? Really, I think the answer is not being able to summit Mount Everest, or even really summit Mount Kosciuszko, but rather a lot of tenacity, the willingness to be wrong a lot of the time and collaborate with folks. You really do want to have an encouraging environment, and all three implementations, to my knowledge, really do foster that kind of an environment that's collaborative and encouraging. And when you make mistakes, everyone really does help you out to get the best possible experience for the users, but also for you, the implementer. And so I'd like to ask that you join us. These slides are not up yet. Please wait until after the break for them to be available, but you can find them at slides.cjdb.xyz. There will be quite a few links that will be available that you can click on. These are the onboarding pages that will be available. And with that, hopefully you have a better idea of what it takes to implement the standard library. Thank you. Sorry?
You forgot masochism.
Oh, yes. Marshall said that I forgot masochism. I will happily take questions now. Nathan.
Yeah, so this isn't really a question, but it's a piece of lore that probably most people don't know. Is that CppNow, when he proposed the STL to be put into the standard library, he was sure that the committee would cut it and would trim major parts, and so he put in sacrificial parts. And priority queue and deck are examples of sacrificial parts that he thought the committee would trim away when they accepted the proposal.
I have heard that before too, yes. Thank you for sharing that. Are there any other questions or comments? Yes.
So you said that the standard libraries are tied to the compiler.
Yes.
But, how much can you use libc with VCC?
So the question is, because the standard library implementations are tied to the compiler, how much can you use libc++ with GCC and libstd++ with Clang? Is that
Yeah.
Yep, cool. So both implementations do go out of their way to provide as much support as possible for the other compiler. Sometimes we do kind of miss the mark, but more often than not, both standard library implementations will work with the compilers to ensure that that there's cross-compiler compatibility. So, for example, let's say that I were to put something in Clang and GCC hadn't got around to implementing it yet. What libc++ would probably do is an if-def to say, well, if this feature is available, use the compiler built-in, and if it's not available, use the code that we've got here. And then when GCC supports it, along with the modular support that libc++ has, that code would eventually disappear because it's no longer necessary, because both compilers support it for all the versions that are the compilers that libc++ supports. Konstantin, do you agree with that statement?
Yeah.
Cool. Sorry, Marshall. I figured that.
I was scratching my head.
Cool. Yep.
So this talked a lot about the, I guess, official standard libraries that are packaged with the compiler that they're being distributed with. What are your thoughts on external third-party standard library implementations that may or may not have varying degrees of conformance with the actual standards?
So that's a good question. What about third-party implementations that may or may not have complete conformance with the standards? And that's a really good question. If you are deviating a little bit, it's no longer standard. I'm a big fan of experimenting and getting users to identify what their needs are. And just because something is not in the standard doesn't mean that it's not useful. It just means that it may not be useful for as many people as possible. Now, the compilers can't go out of their way and support every possible third-party implementation, but if there is a feature that is going to be really beneficial to many implementations, then perhaps they could bring forward a patch that would help. And if that's not the case, then they could always keep a patch locally in their own version of a compiler that's like, okay, well, if you want to use this particular implementation of this feature, you need to build your own version of the compiler. Does that answer the question, or did I leave like a little gap there? Cool, thank you. Yep,
when
Jeff?
you're on Windows with the Clang setup, is that using MSVC's library or is it using libc++?
That is a very good question. So that what you're asking is if you're on Windows with Clang, are you using libc++ or MSVC's STL? Marshall, sound like you've got an answer?
Well, I have an opinion based on outdated experience, but you want to use the Windows Standard Library implementation if you're going to link with any shared libraries that were built, say, with MSVC, because they'll be using the Windows Standard Library implementation. You don't want to take a libc++ vector and pass it to something that expects, say, MSVC vector.
Right.
Yes, that is a very good point.
So there, I guess the point was that there's even another level of compiler compatibility there, right? Because Clang is supporting that library as well at some level.
So I believe you need to use the binary called Clang CL, which provides the Microsoft front end for Clang.
Okay.
And so you can use libc++, and I'm getting signal that using MSVC's STL with Clang CL is also possible. Clang does have a lot of machinery in it that lets you use has a fair bit of machinery in it that makes it as if you're using MSVC's front end. For example, the built-in for isSame there are actually two built-ins that do the exact same thing. One for Clang and GCC compatibility, and one for MSVC compatibility. So I think the answer is that you can use either one based on all the data that's available to me. Does that answer the question?
Yeah.
Cool. Ooh, few hands. Okay, so I saw that one first. Then I think I saw two over here, but they were a race condition.
Okay, I'll go for two.
Okay.
So for the benchmark, you recommended to turn on the PGO.
Yes.
From my experience, like when you have like an optimization, new optimization, it hasn't been simple yet. So the PGO kind of like penalized the new implementation. So like, is there any like recommendation on like how like you use the PGO for benchmarking? So
that is going beyond my area of expertise, unfortunately. I am neither an expert in PGO nor in extreme benchmarking. I know how to write benchmarks, barely, but I know how to tap into people's knowledge and get them to help me understand benchmarks and what to do. So unfortunately, I don't have a good answer for you there. I'm sorry. Okay, so who won the race condition?
We agreed I get to go first.
Okay.
One thing I've seen with standard library implementations that most libraries get to ignore, the additional complexity of dash stud equal whatever. And I've seen standard libraries tend to go out of their way to make that ABI compatible across things where everyone else doesn't, and then it breaks later. But I was thinking about this when you mentioned, well, you need to reference the working paper. You actually end up needing to reference a whole bunch of them.
Yes.
Because at any point in time, the working paper is just this standard.
It was very difficult for me to take out the C++ 11 through 23 that I had and just condense it to the working paper because of exactly what you said. I was confused.
The other thing that I've seen is like, because I was proposing some changes to optional.
Mm-hmm.
I got to just read out of the standard a current base implementation that like was really nice and stable. It's like, because I could just turn the mandates into static asserts and use requires clauses. And then I looked back at what the actual standard library implementations have to do, and I felt so bad for.
By the way, you're quite welcome. I wrote the papers that basically took all the requirements and turned them into mandates and constraints. So I basically rewrote 1,000 pages of standardese.
Yes, thank you, Marshall, for doing that.
Yeah,
And thanks to everybody in the committee who had to review them to find the typos I made.
Yeah. What is the expectation for module support in the libc++ and the libstdc++?
I believe it's still experimental.
Okay. I mean, is there an expectation of when that will actually ship as?
To my knowledge, Clang and possibly GCC, I don't know. Well, actually, you'd know better than me on GCC's front. Doesn't have full module support yet, so libc++ would have to trail that. But Konstantin, do you have any idea? Still.
Unfortunately, I can't say off the top of my head. It's definitely something that's being actively worked upon, but I don't know the exact timeline. Actually, if you can catch me in the hallway, maybe we can exchange contacts. I can point you to our proposals and things like that.
Thank you. Hannah?
Clang 18 and libc++ 18 supports student modules.
Straight out of the box?
Yeah.
Oh, okay. That's, whoop. Well, I guess you get a photo of the Harbour Bridge now.
Clang 18 and libc++ 18 supports student modules.
Nice.
So, yes, just for the microphone, just in case it didn't get picked up, the Clang 18 and libc++ 18 have something straight out of the box, which is fantastic. Thank you for bringing that to my attention. Okay, are there any other questions? Because, yep, last question.
Yeah, you mentioned that C++ has a mode which lets the user control like stability versus performance versus environmental, etc. Are there any other like modes or like tips that you can give us for ways to tweak or set the libc++?
So that is a really good question and one that I cannot answer in under a minute. But what I will say is that A, I'm happy to chat in the hallway track. B, this is the first half of the full talk that I'm planning to give. The other half is not as C++ now. It's still being designed. And C, the libc++ documentation actually has a full list of all the supported macros, and that is a good way to identify what flags are at your disposal.
Some of the stability flags, the ABI stability kind of things, are not there for users to play with. They're for the people who package up the standard library and ship it with their OS, because all the other pieces of the OS are built with that particular ABI.
So it is good to check the documentation and understand which things are for you, which things are for vendors. So thank you, Marshall, for that last bit. Okay, thank you very much. I'm more than happy to